This is a production of Cornell University.
So those are the constraints. How about some of the competitive advantages? Now, as we've been talking about these constraints, I've been talking about competitive advantages. Nitrogen fixers, for example. Let's talk about nitrogen fixers. Okay? Biological nitrogen fixation basically takes this N2, converts it into an ammonium, NH3, and they put it into organic compounds as an amine, an NH2. Okay? Now, this process consumes energy, so I have to put energy into this. If I'm a microbe that can do this, I have to put energy into this. Which means if this is available for everybody, this is not an advantage to me anymore. Okay? Yes, when there isn't this available, this is a huge advantage. So you have to think about the scenario that these competitive advantages are in fact advantages. Okay? There are several groups of bacteria that have this ability, and it's most effective, though, or most efficient, not effective, most efficient in symbiotic relationships. Now, think about this. Why would we say this? Now, this might not, in fact, be true, but why would we, in fact, say that? Why is it most effective in symbiotic relationships? Right. So if I can do the nitrogen fixation, and in exchange for doing nitrogen fixation, you're going to give me the carbon, as well as the other nutrients, that's a serious advantage. Because now I can specialize. I don't have to worry about getting anything else. All I need to do is do my job and get nitrogen. Right? Or take nitrogen and put it in usable form for the organisms that I'm transferring it to, as well as myself. Okay? So now I'm in a partnership relationship. I'm getting something good, he's getting something good. Okay? Autotrophy is another serious advantage. From an energy sense, it's a great advantage. Basically, we're looking at things like phototrophs or lithotrophs. If I'm a phototroph, I'm basically getting my energy for free from the sunlight. Okay? I don't have to do a lot of work. I just sit there and get a suntan. Okay? Now, can you think of some limitations there, though? Shade. I certainly have a landscape distribution that is very limited to me. I can't go very far down. And if I'm underneath shade, other organisms that are basically doing the same thing, there can be fairly fierce competition for this sunlight. Okay, how about lithotrophs? Lithotrophs are basically getting their energy from inorganic oxidation. They're not getting it from carbon sources. They're not getting it from sunlight. They're basically taking something like this and converting it to this, taking something like this and converting it to this. Okay? In essence, they're avoiding competition for organic material. But the bad component of this is that I may be not getting as much energy as the organisms that are using the organic sources. Yes, I'm getting energy. If there's no organic material around and I can get my energy this way, you know that's a serious advantage. Right? Or I should say, there's no usable organic material around. All right, how about opportunism? This is a big one, and most microbial populations have this. And this is basically the ability to respond very quickly to a change in the environment. Okay? Both beneficial as well as detrimental. But in this scenario, we're basically looking at beneficial. If a food stock comes in and I can increase my population within an hour, you know I'm going to be reproducing. And if I'm reproducing, that's evolutionary success in essence. I can also inhibit production of other organisms. Okay? Bacteria and fungi have a lot of, this is a lot of where our antibiotics come from. They can produce different materials or compounds that they can release into the environment, which basically inhibit other organisms. Okay? This is where we get penicillin, streptomycin, tetracycline. Okay? Penicillin comes from fungus. Actinomyces is the streptomycin, tetracycline sources. These names should be fairly familiar to you guys, right? Okay. I also have a lot of organisms that can have specialization. Okay. They avoid competition because they use a carbon source that's not available to anybody else. A good example here are the wood-rotting fungi and bacteria. Again, going back to when was the last time you ate a log. Okay. These guys can take advantage of this. There also, it turns out, because of the nature of the material, plastics and petroleums and pesticides products, because of the carbon nature of them, there are a lot of specialized microbes that can, in fact, degrade that material. This is a lot of those pseudomonases that I was talking about earlier. Okay, those guys that can basically chew up 100 different types of compounds. Pseudomonases have a lot to do with this kind of decomposition. Then we go back to the symbiotic relationships that sort of we talked about with nitrogen fixation. There's lichen, there's N2 fixing legumes, and there's mycorrhizal relationships. Not all of these symbiotic relationships are nitrogen components, but often they are. The lichen are basically algae fixing with algae and a blue-green bacteria that are basically living within fungi. Okay? The algae fix nitrogen. The fungi give the bacteria water and mineral nutrients. Okay. We also have nitrogen-fixing legumes, where we're looking at rhizobium that are fixing nitrogen, giving it to the plant, and the plant in turn provides water and nutrients. Okay. We also have other kind of mycorrhiza type of relationships, where it's not necessarily nitrogen, but it could be other type of nutrients. Phosphorus is a good example here, where the fungi, because of its hypha, actually has a larger root area in essence, so it's expanding the root area of the plant. And then the plant, in turn, provides organic food to the fungi. Okay? A lot of these types of relationships out there.
This has been a production of Cornell University, on the web at cornell.edu.